In this webcast, we look at an elevator lab, which is the subject of worksheet 5B. So in this activity, we're going to look at how forces change on a person as they ride in an elevator. And so a man has taken a set of bathroom scales with him into an elevator, and he records how the reading on the scale changes as he goes up 20 floors, and then as he comes, 12 floors, and then as he comes back down 12 floors. So let's watch the video that shows how his weight is changing. So here we see that when he's at rest on the ground floor, this is the beginning of the video, his weight is 202 pounds. Notice here, before we start the video, how to read the scale. So there are 5 divisions between 200 and 210. So each division on this scale is equal to 2 pounds. Okay, so his weight when he's at rest on the ground is 202 pounds. And now I'm going to start the video, and he's moving from the ground floor up to the 12th floor. So here we go. Oh, his weight is changing. It went to 222. Then back to 202, then to 186 it looks like, and then it returns to 202. Okay. And so I've recorded these observations in the table in this worksheet. So again, at rest on the ground, he weighed 202 pounds. And then the reading increased while he was moving up to 222 pounds. Somewhere in the middle, on his way to the 12th floor, the elevator reached a constant velocity, and the scale showed his weight as 202 pounds briefly for that period. And then this elevator had to start slowing down as it neared the 12th floor, and the scale reading changed to 186 pounds, and then when he was finally at rest on the top floor, the scale again was 202 pounds. In this lab, we are going to work in metric units, and so one of the first things I've done is to convert the man's weight in pounds into his weight in newtons, and I use the conversion that there are 4.5 newtons for every pound. Okay, so we've got those converted. Now I'd like to look at his return trip, starting from the 12th floor and going back to the ground. So here he is on the 12th floor at rest in the elevator, and the scale is showing his weight as 202 pounds. Okay, so he's going to start moving back down to the ground floor. Oh, look, his weight went down to 180. Then it comes back to 202. Then it goes up to 216, I think. And then as he got to the first floor, he went back to 202 pounds. Okay, so now I have recorded those observations in the right-hand side of this table. So what the scale is reading as the man moved from the 12th floor back to the ground floor. So the scale reading changes a lot during this trip up to the 12th floor and back down. But do you think that the man's actual weight changed? I don't think that it did. And so something else is going on. Let's do a force diagram on the man to figure out what are we seeing when we read the scale. So the force diagram is very simple. There is the force of gravity that the earth is exerting on the man. That's the man's actual weight. And then there's also a normal force that the scale is exerting on the man. He's standing on the scale, and the scale is supporting him. And so we have that normal force. So when we read a scale, we're actually reading the value of the normal force that the scale is exerting on the man. The man's weight makes a small spring in the scale deform, and based on the deformation of that spring, the scale is calibrated to show an amount of weight. Okay, so we know that when we look at the scale, we're actually seeing the normal force that the scale is exerting on the man. Let's look at the situations where the scale reading matches what we believe his true weight is. So when he's at rest on the ground, the normal force and the gravitational force equal. And so here, he's at rest on the ground, his weight is 202 pounds. When he's at rest on the 12th floor, his weight is 202 pounds. Same thing, you know, on either end of the trip when he's at rest, the scale reads the same thing. But look, it also reads the same thing when he's moving at a constant velocity, either up or down. So when he's at rest and when he's moving at a constant velocity, the scale reads his actual weight. And so we can summarize a rule for that. You know, when does the scale reading equal the person's weight? That happens when the elevator is at rest or when it's moving at a constant velocity. In those situations, the net force is zero. We know that from Newton's first law. And so the normal force, which is the scale reading, equals the man's weight. Okay, now let's try to make a general rule for when the scale reading is less than the man's weight. Okay, so let me get a different colored pen. Maybe we'll use purple for this. Okay, so let's see. Here's a situation for that. The scale reading is only 186 as the man is getting close to the 12th floor and the elevator has to slow down. So in that situation, the man is moving upward, right? He's on his way up to the 12th floor, but he's slowing down. And since he's slowing down, acceleration is in the opposite direction, and so acceleration points down. So that's one of these situations where the scale reading is less than his weight. Here's the other situation where the scale reading is less than his weight. In this situation, he's starting to move down, coming back to the ground floor, so his velocity vector is moving downward. But since he is speeding up at that point, he was at rest and now he's starting to move, so he's speeding up, his acceleration is in the same direction as the velocity, which is also downward. The thing that's the same for these two situations is that acceleration is in the negative direction. So our rule, we can generalize, says that when acceleration is negative, the scale reading is less than the man's actual weight. Acceleration is negative either when the elevator slows down as it moves upward, or when the elevator speeds up as it moves downward. And now finally, let's make a general rule for when the scale reading is greater than the person's weight. So let's see, let's get another color here, maybe orange. Okay, so one situation is right here. As the man started to move upward from the ground floor, the scale reading increased to 222, and that's more than he actually weighs. So he was moving upward and his speed was increasing, so acceleration was pointed upward. Another situation is right here where he was moving down toward the ground floor and the elevator was beginning to slow down because it was approaching the place where it needed to stop. And so here he is moving downward, so his velocity vector is in the negative direction. But also, since he is slowing down, acceleration is in the opposite direction as his velocity vector, and so acceleration was up. What's the same between these two situations is that acceleration is in the positive direction. So our general rule for that situation is that when the acceleration is positive, the scale reading is greater than the man's actual weight. Acceleration is positive when the elevator speeds up as it moves upward, and when the elevator slows down as it moves downward.